All right, we'll start with some announcements. Homework 1 is available on Canvas. Homework 1 involves decision trees. By the end of today's lecture, you'll have all the material you need to completely do homework 1. You'll be implementing decision trees, you'll be running a bunch of experiments. And what I have found is historically, this homework takes a lot of time. Not because it's difficult, maybe it is, but actually that's not the real reason. Because this is the first homework, there's always some impedance with getting things set up. There's some sort of a barrier to running your code in the right way and such things. And to avoid all of that happening at the very end, I would recommend starting as soon as possible and using Piazza and the office hours for any support that you need. Yes.
Does homework 1 indicate any sort of specific environment set of things?
Yes, that's the next thing I was going to mention. We have given you some code skeleton in Python that you can fill up. You'll need to implement certain functions, and if you just keep the skeleton of the code as it is, GradeScope's auto graders will be able to grade your assignments. Otherwise, we'll have to run it manually and such things. So there is a skeleton in Python. I'll talk about this in a minute, but most of you are comfortable with Python apparently. In fact, that's the next thing I was going to mention. This is from your survey. Nearly all of you are familiar with Python. So most of you would be able to use the code skeleton that we gave you. If you cannot and will not use Python for some reason, you will still upload your code on GradeScope. It will be manually evaluated by the TAs. If it's a language that none of us are familiar with, then we can't give you partial credit in such things. If you're using Python, you are allowed to use NumPy and Pandas and a small set of libraries that we've listed in the code that we've provided. In particular, you are not allowed to use any machine learning library. That should be obvious, right? I mean, otherwise, what's the point? So, and if you do use any machine learning library, your code will not get automatically executed on GradeScope, and then someone will have to look at it, and then they'll find that you've used a machine learning library, and you won't get your points. Okay, start soon, start early, and in fact, after this lecture, you'll have all the material you need for that class. So for the homework. Are there any questions? Any other questions? There's also a theory part where you'll be working through the decision tree algorithm. We'll be looking at the decision tree algorithm today. In some detail, you'll be essentially doing something like what we are doing in class on a data set that we've provided. Also, thank you for those of you who filled out this survey. Been very useful to get to know you all. As a fun exercise, I just pulled out from that survey all the answers that you all wrote for the last question, which is, what do you do outside of class, any fun projects, and so on. And I put them all together into one slide. And you are an interesting bunch. The font size is small because I couldn't fit everything in otherwise. But there are many, many interesting things that you all collectively do. Some of my favorites is someone in this class has finished their own basement. And someone in this class has built a system that can track the moisture level of plants and waters them automatically. And there are a bunch of video games being written, a bunch of large language models, and it's kind of cool stuff. So, this is you all. If anything here interests you, oh, someone built a Rubik's Cube solving machine. I love that. So if anything here interests you and you want to know more, I don't know how you all meet each other, but figure it out. Okay, are there any questions? Not about this, because that's pretty much all I have to say. Any questions about the homework or any logistics? Yes.
Yeah, how is homework 0 going to be graded? Because I just understood it. I don't remember fully understanding it. Was it just like So like making sure that we.
So homework 0 will count to maybe well, maybe 1% of your final grade. It's not a significant amount. It's mostly originally when I designed homework 0, I decided that it's worth 0% of your grade, and nobody did it. So it's a tiny thing. The main motivation here is for you to figure out things that you don't understand and maybe look up or come talk to us so that we can kind of guide you through it. Some of those things will form the basis of some discussions that we'll have through the semester. And if there are specific things that you don't understand, you can post a message on Piazza. We'll send you resources related to that. Okay. There is a question in homework 1. Is there a question that we are supposed to work through on pen and paper, or are we supposed to do coding for that as well? So really the homework has two parts. There's one part that is pen and paper, where you work through mostly to understand the mechanics of the algorithm. And the second part involves implementing things in code. Oh, and grad students also have an extra question. Purvit, you had a what? Oh, yeah. Pen and paper does not mean pen and paper. Hopefully there is neither pen nor paper involved in this. It's mostly you typing the answers on in a word processor. Please don't write your answers and submit it, especially for the mathy parts, because I truly do not expect to understand your handwriting. And, I feel for my TAs. Yes. It's subjective. I'm sure you do, and I'm not saying you don't, but I would much rather prefer that you typeset your answers. Yes.
Is the graduate homework inside the homework?
Everything's in the same PDF. I think question 3 is for grad students only. And a question that I get often is, if an undergrad does that question, will they get extra credit? The answer is no. Other questions? Okay. If there are no questions, we're going to pick up where we left off. In the last lecture, okay, that's scary. Can people on Zoom still see what's going on? It's very blurry. How about now? Actually, if my okay, good. Okay, so in the last lecture, we looked at this algorithm called ID3, and I do not know why it's. Yeah, we looked at this algorithm called ID3, which is a decision tree learning algorithm. And we haven't finished the entirety of the algorithm, but very quickly, the general idea of the algorithm is the following. If you're given a data set, and if every example in the data set has the same label, remember your data set consists of examples. And because we are operating in the supervised setting, every example consists of a bunch of features and a label. And our goal is to build a system that can use the features to predict the label. So if every example in your data set has the same label, then you really don't need to look at any of the features. You can build a leaf node with just that label. That's the base case here. Otherwise, you need to actually grow a tree. And the idea is intuitive once you start thinking about it. If you ever want to build a tree, if you want to build a tree procedurally, you need to construct the root, and you need to somehow recursively construct all the children of that root node. So in a decision tree, every inner node corresponds to a feature, a test for a certain feature. So building the root essentially says is equivalent to deciding a single attribute that best classifies the data, partitioning the data into subsets according to that feature, according to different values that the feature takes, and then underneath that, growing subtrees using only the subset of the data corresponding to that feature. So that's the recursive call here. Below that, you add the subtree. We went through this in some detail. I'm not going to repeat all the intuition here, but the thing that we left unspecified is this part here. How do we best classify the data? How do we pick a single feature that best classifies the data? And that's where we're going to pick up today. The goal is to pick what I'm calling the root attribute. And the heuristic that was developed by Quinlan to define this algorithm called ID3 tried to operationalize and the following intuition. We seek to build decision trees that are as small as possible given a data set. Why? Because smaller trees are less likely to memorize the noise in the data. If you allow a tree to grow arbitrarily large, it will end up memorizing not just the signal, but also the noise. So smaller trees are less likely to memorize the noise. As a result, they're more likely to overfit. Sorry, not overfit, but more likely to generalize better. And to make this intuition into something you can implement, the original ID3 algorithm used a notion called information gain. And that's what we're going to define next. Any questions about the high-level algorithm or this intuition that smaller trees might be better? If there are no questions, let's dive into this part of this. So the idea of information gain has its roots in information theory. The key concept that's worth keeping in mind here is the notion of entropy. Some of you may have seen entropy and some of you may have not. If you've seen entropy, consider this a reminder. If you've not, consider this an introduction. I'm not going to talk about entropy in the most general sense, in the sense that's used in information theory. I'm going to talk about it with respect to what we need here. So let's say that you have a data set. And let's say that you have a data set for binary classification, where the fraction of examples that are called positive, that are labeled positive, is p plus, and the fraction of examples that are labeled negative is p minus. So p plus and p minus together add up to 1. The goal here is to identify how pure or impure this data set is with respect to the labels. So for instance, if p plus and p minus are both equal to half, that means half the examples are positive, half the examples are negative. If you pick a random example, it's a coin toss. You can't tell whether it's positive or negative. On the other hand, let's say that in your data set with maybe 100 examples, 99 of them are positive and only one of them is negative. So then p plus is 0.99 and p minus is 0.01. So yes, these are the labels attached to the examples. These are just two categories. So if you have 99% positive and 1% negative, it's nearly entirely pure. If you pick a random example and you guess that the label is positive, you'll be right 99% of the time. So in some sense, this way of partitioning the data is in some sense cleaner than the other one, which split it 50-50. More to formalize this notion of a disorder or impurity, we have this definition of entropy, which I'm just going to read it out. It is the negative of p plus log p plus minus p minus log p minus. So there's no point in staring at it as an equation. Let's kind of work through what it means. First of all, this can be generalized to if you have more than two categories, it's simply the sum over all the categories of pi log pi and slap a minus sign at the top. And all the logs here are log to the base 2. Why? Because of historical reasons. We don't need to go there. But let's see what this actually does. Let's consider the case where all the examples belong to the same label. So let's say all examples are positive. So p plus is 1 and p minus is 0. So let's work through what's going on here. P plus times log p plus, log of 1 here becomes 0. So this term ends up being 0. And the second term is p minus times log p minus. It's really 0 log 0. Log 0 is negative infinity. It's an indeterminate form, but for technical reasons, turns out this also ends up being 0. It's 0 times something. So if your data consists, if the proportion of positive and negative is such that everything is one label, everything is positive, then the entropy is 0. The way to think about it is the amount of disorder in that data is 0. Another way of thinking about it is the amount of information that you need, the number of bits that you need to transfer in order to convey the label of any one random example is 0. You don't need to give any information to convey the label about any example in that data because everything is positive. I remember seeing an intro to, I think, AI book or something, a useful sort of a way to think about entropy. Suppose you have a weather station in Antarctica, and it's one of these weather stations that does not actually give you the temperature or anything. It only says whether it's really cold or really hot. Those are the two things that the weather station conveys. Do you actually need a weather station in Antarctica? Does it ever need to transmit anything? Because it's always really cold. So the amount of information that's needed to convey anything about the weather, if it's only these two things, is 0. The number of bits that need to be transmitted is 0. On the other hand, let's say you have a weather station somewhere like in Salt Lake City, where on some days it can be really cold, some days it can be really hot. So you need to actually convey information. So the amount of uncertainty in the weather is, in this case, it's 1 bit. Maybe it's 1 bit. It's if it's 50-50. In fact, let's consider the case when p plus and p minus are both 50% half each. So it's this, p plus is half and p minus is half. Then let's work this out. It's minus half log 2 to the base of half minus half, right? So here's a useful way to think about it. Log to the base 2 of 1 by 2 is what? It's minus 1. So it's minus 1. So this thing becomes minus 1 and this thing becomes minus 1. So the whole thing adds up to 1. So if p plus and p minus are both half, then the entropy is 1. If there is absolutely no way to tell, given a random example, if there is no bias towards any one label, then for a random example, you need to convey 1 bit of information. So entropy can be thought of as the number of bits of information that need to be conveyed for a randomly chosen example to about the label of a randomly chosen example. So, like I said, if the probability is 0.5, then 1 bit is needed. If the probability of plus is 0, then, or if it's exactly 0 or exactly 1, then 0 bits are needed. If it's in between, then on an average, something between 0 and 1 bits will be needed. Any questions? I saw your hand first, and then I'll come to you. Yes.
Kind of counted we know because we're considering a number of bits between 0 and 1. That's a real value number.
It's that's I was thinking of that when I said that, when I said somewhere between 0 and 1. It's on an average, if you have a long transmission of, you keep sending many instances, so you can kind of encode the information so that multiple examples can be packed together. So on an average, over a long term, you only need less than 1 bit. It's an expectation. Yes.
So, kind of two questions. One is the range of entropy in this case from 0 to 1, and 2 is maximized when you have equal proportions?
That's a excellent question. In fact, I might actually be talking about that very soon, but the short answer is, if you have a probability distribution over 2 outcomes, then the maximum it can be is 1. If you have a probability distribution over 3 outcomes, the maximum it can be is log 3 to the base 2. So if you have k outcomes, it's log k to the base 2. What's your second question?
Oh, I guess there was like 2 questions.
Oh, okay. Did someone else raise a hand somewhere here? Did I miss something? If not, we'll move. So here's another way to think about it. Uh-oh, what did I do? So here's another way to think about it. If your probability distribution is even, meaning both the pluses and the minuses are equally likely, then the entropy tends to be higher. If the probability distribution is uneven, then the entropy tends to be lower. And somewhere in between, entropy will be in between. And if the probability of the label is all the labels are equal, that is the most uncertain that you can be about the label. Or that's the kind of data set where the impurity or disorder is the highest. Whereas if it's uneven, the impurity or disorder tends to be lower. Okay? You can generalize this also to multi-class. In general, the uniform distribution has the highest entropy. So if you have 3 distributions of this kind over multiple categories, the uniform distribution tends to have the highest entropy. It does not have to be 1. So if the number of categories can be, if the number of categories is more, the entropy tends to be, can be more. If you want a short summary of everything here, higher entropy corresponds to higher uncertainty, lower entropy corresponds to more certainty or low uncertainty. Or higher entropy corresponds to higher disorder, and lower entropy corresponds to lower disorder. Any questions?
Does that mean the higher the entropy, the data set is of low quality?
No, it's not about quality. It's not about quality as much as it's about the uncertainty in the label given no information about the features. So the quality of a data set depends on things like noise and errors and such things. But it's entirely possible that, let's say that I assemble a data set of images, and I have half of those images have cats and half of them don't have cats. And I have spent a lot of money and a lot of effort carefully making sure that every image that's called a cat actually has a cat, and every image that's not called a cat does not have a cat. So it's a high quality data set. There's no noise. But because my data set is equally split between cat and no cat, it will have high entropy. In this case, it will have entropy equals 1, because it's the highest you can have for 2 categories. It just means that given a random image, and if I hide the image and I don't show you what it is, you have no way of knowing whether it's cat or no cat. It's the highest uncertainty about the label, unconditional without being conditioned on the input. Without knowing the input, the label is maximally uncertain, because given a random image, let's say I take a random image and I hide it from you, and I ask you what's the label. Can't tell. But on the other hand, if I create another data set which has 1 million cat images and 1 no cat image, and I take a random image and hide the label, you can guess it's not a cat.
So only preferred data set knows low density.
No, we don't have a actually data sets with low entropy are useless, right? Because for the most part, all their examples have the same label. So they're not useless, but essentially it just means that the label distribution is uneven. The entropy idea will not be used for data cleaning and such things. It's mostly used for deciding how to partition data sets for decision tree. That's really where we're going to use it. Did you have a question?
Yeah, I did, but I think it was kind of answered. So isn't a low entropy data set essentially bad because we have less examples?
But sometimes nature does that. Sometimes nature does that. Let me give you an example. Suppose you want to create a data set where every word, let's say it's a data set of sentences. For every word in the sentence, you want to decide whether that word is grammatically correct or not. The usage of that word is grammatically correct or not. It turns out that if you construct that data set of that kind, most words are grammatically correct. 99% of the words that most people use are with people of at least reasonable language skill. Most of them are going to be correct. But the interesting part is in the 1%. Because if you want to build a grammar corrector or a grammatical error detector, you care about that 1%. So it depends on the nature of the problem. Okay. So the reason I introduced entropy is to introduce this information gain heuristic for the decision tree algorithm. We've still not resolved the question of how to pick the root attribute. And the intuition behind the ID3 heuristic is we consider every possible attribute and pick the attribute that if you partition the data according to that, it maximally reduces the entropy. The partitions are as pure as possible. That's the goal. So let me illustrate, let me formalize this idea, and then we'll look at an example. The key point here is something called information gain. The information gain is a feature, is a property of an attribute. In this, for some historical reason, in this unit of the class, I'll be calling features attributes because that was the terminology that was used in that era. So the information gain of a feature is, or an attribute, is the expected reduction in entropy that you get by partitioning the data according to that attribute. So if you have a data set S, so let's say we have a data set, I'm going to call this box this box contains the data set. There are some pluses here. And maybe this is all feature, the feature A takes the value A1 here, A2 here, A3 here, and A4. So the entropy of the data is the entropy of the entire set S. So this whole thing is S. So you have a collection of examples, some of them are plus and some of them are minus. You can calculate the entropy of that data. So that's the original entropy of the data. And then let's say you partition the data according to attributes, according to the attribute A. And here, let's say the feature A takes 4 values, A1, A2, A3, A4. And all of these are A1, all of these are A2, and so on. Let's consider A2. When you split the data according to feature A2, you get a bunch of pluses. What's the entropy of that data? It's 0. Because there's no uncertainty in the label in that subset. Similarly, when you split according to A3, everything's a minus, so there's no uncertainty there either. And then you have A1 and A4, which has some non-zero entropy. So that is this bit here, the entropy of the subset. And the information gain is simply the original entropy minus the average entropy of all the subsets. It's not average equally weighted because you see this subset A2 and A3 have more examples. So it should have a increased importance. So this S, the SV, the size of SV divided by the size of S is simply the fraction of examples that belong to that subset. So it'll have 5 divided by, so if you have n examples here, 5 divided by n times 0 plus 5 divided by n times 0 plus times the entropy of this, plus similarly for the first part. So that is the expected entropy of the partitions, and the information gain is the original entropy minus the expected entropy. So you started with this much disorder, and then you partition the data according to this feature. Each subset has some entropy, and you can compute the average entropy. How much uncertainty have you removed from the data by splitting according to this feature? That's the information gain of this particular feature. I know there are two kinds of people in the world. One who sees an equation and understands what it is and how to use it, and another one who sees an equation and thinks, what? I know that more people belong to the second group. So the way to interpret this, there are a few different ways to kind of look at these kinds of expressions. The first one is just to see what it is mechanically. Don't worry about interpreting it. Literally understand what's going on. It's simply the entropy minus the expected entropy of the partitions. But really, the best way to interpret these sorts of things is actually to look at some examples. So we'll be working through an example where I instantiate each of these things. I'll do that a few times, enough number of times that hopefully you get bored of it by then, at which point you probably get it. So the entropy of the subset, you assign a weight to each partition so that larger subsets have a bigger play a bigger role. We'll see what this means. Once I'm done with this, I would like you to go back to that example. Remember that example where I had 4 splits, four labels, this example here, where you have 2 features A and B, and you have this subset. I encourage you to go back to this example after we finish this lecture and compute the information gain of A and B to see whether A or B is preferred. The answer should be A. It turns out the information gain does actually capture the intuition that A is better. But to kind of instantiate all of this, let's go back to the tennis data set. As a reminder, the goal here is to decide whether we should play tennis or not based on these 4 features. So we want to build a decision tree. To do that, we need to first decide which feature to split the data on. There are 4 features here: outlook, temperature, humidity, and wind. And the ID3 algorithm needs to evaluate the quality of each one of these features. So let's start with outlook. So first of all, before we do anything, we need to calculate what's the entropy of the data. There are 14 examples here, and 9 of them are positive and 5 of them are negative. So what I call P plus, I've called it P here, and what I call P minus, I call it N here. So P plus N adds up to 1. The entropy is simply minus P log P minus N log N, which is what I've written here. And if you work through the math, you'll see that this corresponds to roughly 0.94 bits of entropy. There's nothing particularly interesting or exciting about that. It's just what it is. But let's now start looking at each of these features one at a time. Let's consider the feature outlook. So that column there. Outlook takes 3 values. It can be sunny, overcast, or rainy, S, O, or R. So the thing we need to do now is partition the data according to this feature. So let's first consider the case where outlook is sunny. So there are these 5 examples where the outlook is sunny, and let's consider only those 5 examples. In this case, among those 5 examples, you have 3 pluses, 3 minuses and 2 pluses. So that you can ask, what's the entropy of this subset of the data? The entropy of this subset of the data is simply the entropy of 2/5 and 3/5, which it turns out is 0.97. Once again, by itself, it's not interesting. It's just the same procedure. You calculate the entropy. You calculate the amount of disorder there is in this data. Now you go to the next feature. Outlook is overcast. There are 4 examples, and all 4 of them have the label plus. That means the entropy of that subset of the data is 0. Because everything, there is no uncertainty left in the label. Then you have one more feature, which is one more value which the feature takes. Outlook is rainy. And there are 5 such examples. Once again, you need to calculate the entropy of 3/5 and 2/5, which comes to 0.97. So what do we have here? We had the entropy of the original data, the full data set, which is simply the entropy of all 14 examples, which was 0.94. And now for each of these subsets, we have these 3 entropies. The information gain is simply, so before with the information gain, we can ask what's the expected entropy of each of these partitions. For 5 of these examples, the entropy is 0.97. For 4 of the examples, so this is for 5 out of the 14th of them, 5 out of 14 examples, the entropy is 0.97. For 4 out of 14, the entropy is 0. And another 5 out of 14, the entropy is 0.97. So the expected entropy is simply the weighted average of all these entropies. It turns out that comes to 0.69. The actual number doesn't matter, but that's what it is. So the information gain is simply the difference between the original entropy, which was 0.94, and this expected entropy, which is 0.69, which turns out comes to 0.24. Any questions about this? I've gone through this a little bit more detail than I usually do for, and I will go. This is not the level of detail that I'll go to for future algorithms, but this is kind of one of these things where it's worth knowing what's going on. Yeah.
So after we perform this information gain for the outlook here, I'm guessing we do this for each of the other attributes here, and then based on that information gain, that tells us which of these attributes to use as the root.
Yes, the root is the feature with the highest information gain.
Okay.
Yes. Yeah.
0.94 is just the entropy for the pluses and minuses, right?
Yes. In this case, whenever for the purposes of this particular lecture, whenever I say entropy, I mean entropy of the label. You can calculate the entropy of the feature value also, but that's not interesting today.
Here you calculate.
No, we are calculating the entropy of the label. So here, this thing here is the entropy of the label for the subset of the data where the attribute takes this value. So in particular, the thing that I just highlighted is only using those 5 examples. It's still the entropy of the label for that subset. Other questions? So now I have something that I'm calling the information gain of this particular feature, Outlook. I can do that for every feature. I can now calculate the information gain for humidity. I can work through the same procedure. When the humidity, turns out humidity thankfully takes only 2 values. So high and I think normal. So when the humidity is high, the rows that are relevant are 1, 2, 3, 4, 8, 12, and 14. There are 7 rows, and among those 7 rows, you have 3 minuses, no, 4 minuses. Oh, you can't see what I'm writing here. You have 4 minuses and I think 3 pluses. So the entropy is the entropy of 3/7 and 4/7, which it turns out is 0.98. And you can also calculate the entropy of normal. There are 7 examples again. 6 of them are positive, 1 of them is negative. I'm not going to go through the list. You can do that on your own. And the entropy is 0.59. As a sort of a sanity check, notice that 3/7 and 4/7 is closer to half and half than 6/7 and 1/7. So this entropy is higher. So the bottom, when humidity is normal, it's not full certainty, but it's less uncertain than when humidity is high. So the expected entropy is half the examples, 7 out of 14 have 0.98, and the other half has 0.59. So the expected entropy is 0.78. And the information gain is the entropy of the full data, which was 0.94, minus the entropy of the expected entropy of this partitioning according to this feature, which gives us 0.15. Any questions? By the way, this, what I'm doing here is something like what you'll be doing for the first part of your homework, where you'll be working through this procedure. And the reason for doing that is because when you do that, it will make your implementation, you'll have a better idea of what your implementation is later on.
And if we're choosing the root node, and choose one of the lowest value.
The highest value. You want the most information gain. You want to reduce the entropy as much as possible using just one feature. So using the, in fact, let's go through that. So I'm not going to bore you with doing this for the other two features. Should I? Oh, good job. Thank you. I don't have the slides for that, and I would have to do that calculation on my own. Will you trust me when I tell you that the calculations give you these entropies or information gains? So you have these four information gains: outlook, humidity, wind, and temperature. And the information gain for outlook seems to be the highest. So information gain for outlook is 0.24. And the intuition here is if you partition the data according to the feature called outlook, you get subsets that are more pure than when you partition the data according to these other features. Because that's the amount of entropy that is taken away, that is eaten up by the partition, by this split is much more. So the heuristic says, once you, because of this, because the information gain is highest when you partition on outlook, you split the data, the root node becomes outlook. That's the intuition here. So you split on outlook. And that means you're starting to grow the tree with the root feature being outlook. And outlook, it turns out, takes three values. Does anyone remember what those three values are? Sunny, overcast, and rainy. And each of those are going to be the values that you'll, the tests that you'll apply. Sorry, each of those branches corresponds to each value that that feature takes. Yes.
Then, just sort of continuing the tree, once we go down one of those branches for the outlook,
Mhm.
would we do this information gain process again on those remaining attributes to decide where to split then?
Exactly. That's exactly what you'll do, and that's exactly what we're going to do now.
Is it possible that across different branches, we might be splitting on different attributes?
Absolutely, yes. Because it's independent runs of the ID3 algorithm.
Right.
So there's no reason that won't happen. In fact, that's going to happen now. So, oh, sorry, was someone else? Did someone else have a question? Did you have a question, or someone at the back? No? Okay. So I can ask which of the examples in this table go into the first category where outlook is sunny. It turns out it is these 5 examples. For overcast, it's these 4, and for rain, it's these 5. And now my goal is to build a subtree under each of these things using only this subset of the examples. So under this subtree, I'll be using row 1, 2, 8, 9, and 11. Under overcast, I'll be using row 3, 12, 3, 7, 12, and 13, and I'll use the rest of them for the third group. And I need an algorithm that can take a set of examples and produce a tree. Do I have such an algorithm? I do. It's ID3. So I can make a recursive call to ID3 using only these subset of examples. Which features are allowed at this point? I've already used up outlook. When I am traveling along this path, the way I have constructed the subset is by considering only those examples where outlook is sunny. That particular feature is useless now because every example in that subset has the same value. So we don't need to consider that example anymore. So we need to build a tree using the rest of the features. So let's kind of work this through. Yes.
This is more of like an intuition question, I guess, but like, is it more likely that, like the first branch, like if there's a feature that has like 10 different options versus a feature that only has 2 different options. Is there like, does it tend to bias towards like first range?
It might. There's a possibility. Imagine that you have a, let's make this even more extreme. Let's say you have a data set of 1000 examples and you have a feature that takes 1000 values. And just so happens, oh, you know what? Let's call that feature example ID. Every row corresponds to, let's say you're splitting on this feature. Of course, you're going to get pure values, except that feature tends to be useless. So you have to be, it involves, there's a certain bit of intuition in choosing which features are even going to participate in this game. Maybe a feature that has a huge branching factor is a little less useful because you'll create small partitions of data which are all pure, but maybe that feature is not going to be very useful in future examples, or maybe it is. Maybe that's the only thing that matters. So depends on the problem and depends on your intuition. Okay, so let's look at these subsets, but let's handle one of these subsets where things are easy. Notice that in all cases where the outlook is overcast, the label is positive. Positive is shorthand for yes. So I don't really need to build a tree. This is the base case. The base case is if all examples have the same label, then you just you build a leaf node with that label and you're done. So this thing is done. Now let's consider the other cases. I'm not going to do the other cases. I mean, I'll leave that as an exercise, but you need to continue till every attribute till one of two conditions happen. Either you've reached a leaf, like here. At this point, you don't need to continue along this, or you've run out of features. You don't have any more features to consider. You've used up all the features and you still don't have a pure split of the data. That just means that maybe the data is noisy or maybe you don't have good enough features. At that point, you just have to pick a label, pick the most common label in that subset, and you're done. So if you go to this subset here, the feature outlook is useless because everything is sunny. And you have these three features, and you need to decide which of them is the best. You can calculate the information gain of each one of those. And I don't know how to get rid of that box now. It turns out that the humidity feature has the highest information gain. You go through the same procedure once more. You split the data according to each feature. You calculate the entropies of the partition, take the expected entropy and the difference between the total entropy minus expected entropy. Do that for every feature. And because you decided to split on humidity, you get two subsets of the data. And once you go to the subset, it turns out in this data set, you'll get two pure subsets and you can get yes and no. Yeah.
Going back a slide with my name, they're using that 0.97. Isn't that the initial information?
Yeah.
Gain information. So
no, that's literally what it means. So if you split on humidity, among all the examples where humidity is high, the label, these three examples where the humidity is high, the label is no. And in these two examples where the humidity is normal, the label is a yes. That means the information gain is 0.97 minus 0. The average of two zeros is 0. That means you get all the information. Basically, by splitting on this feature, you get a perfectly pure subset. And so this is a good feature to split on because it's highly informative. This is the most informative feature, in fact, for this partition. You'll see that in the other case also, if you work it through for rain also, you'll find that the feature wind has a similarly high information gain. And to answer an earlier question that came up, you have three branches here. And notice that in each of these three branches, we have done different things. In the middle branch, we just assigned a leaf. In the sunny branch, we picked the ID3 heuristic, picked the feature humidity. On the rain branch, we picked wind. You don't need to have picked the same feature on both sides. So Any questions about this? I've gone into a fair amount of detail and it's kind of a little tedious detail. So if you have any, yeah.
Yeah, just to clear up, so you need to calculate, the gain after you pick the first root branch.
So it's really just two steps, okay? You pick a root node and you partition the data. And then here you start the process all over again. You pick a root node and you partition the data. And you keep going till you've run out of features to partition on, or all the examples are pure. I saw a couple of heads nodding. I'm afraid that
Saying that like. Things like entropy in order to find information gain, whatever has the highest information gain acts like a quote unquote root. And then from the root, we like split up the like things that it could be, and we just continue doing that until we have every attribute or a breach at the end.
so you keep splitting till your partitions are all pure. Basically, you hit the base case for your recursion, or you've run out of features, at which point you don't have anything else to split on. In which case, you just have to pick a default label for that partition, even though the data set is not pure. And a reasonable default would be picking the most common label. In fact, the most reasonable default is that. Oh, just toss a coin. Use the feature that is alphabetically lower. You just need to have a consistent policy in that case to resolve ties. At least as far as there is no statistical signal to disentangle those two things. So you just make a choice. Yeah.
Also, when there are no attributes to split, and then there are equal number of labels of two types, then even
yeah. Anytime in this algorithm, anytime you encounter equal number of things, you just make you can do one of two things. Either randomly pick one, in which case there's a certain amount of non-determinism in the algorithm, or you pick the one that is the first in some list or something. That way, every time if you run the same thing twice, you get the same tree back. Okay, so let's go back up. Let's step back up a bit. For the decision tree algorithm, the hypothesis space is the set of all possible decision trees. And remember, the set of all possible decision trees includes the set of all possible Boolean functions. So it's a massive hypothesis space. And it has the good news is that if you search over such a large space, you'll be able to find a good tree that fits any data. The bad news is that you'll be able to find a good tree that fits any data, including the noise in the data. So that could be problematic. We'll get to that question in a bit. Our goal is to find the best decision tree, and the ID3 heuristic tries to approximate the intuition that smaller decision trees are good. Ideally, we would like to find the single smallest tree that perfectly explains the data. But searching for the smallest tree that explains the data is intractable, is computationally intractable. So ID3 is really a greedy process. So it picks and the way to think about why it's a greedy search is once you make a decision for a root node and you go down the tree, you'll never go back and say, oh, you know what, maybe I should choose a different root node. Once you pick a root node, you go down and you never go back and correct things. So it's a greedy search. If you've taken AI, another way to think about it is it's a hill climbing algorithm without any backtracking. If those words make sense, that's what it is. If those words make no sense, don't worry about it. Yes.
Why would the root node, like the decision you choose, be greedy if you already found the optimal root node?
It's not an optimal, it's a heuristic. The information gain is just a heuristic. We do not have necessarily the mathematically optimal thing. Maybe it's possible that after you make a choice for a root node, you might go down the tree and think, Had I split on something else, my lower down splits would be cleaner. But you're never considering that in your decision for the root node. And your lower down splits never impact what you choose there. So it's not mathematical, it's not provably optimal. Another thing to note about this algorithm is it makes statistical decisions using all the data, which means if I get one more data point, there's no easy way to go back and fix a tree. You might have to redo the whole thing. There are variants of this algorithm that try to do this in this sort of an incremental fashion, but the vanilla version of this algorithm does not do that. Quickly summarizing this part, we've seen what decision trees are. We talked about the representation, and we just looked at this the algorithm for the learning decision trees. We looked at one algorithm. There are variants of this. The ID3 algorithm is a greedy heuristic. I keep calling it heuristic because there's no guarantee that this will find the smallest tree. It's a very, very simple algorithm. All the examples have the same label, then you create a leaf node. Otherwise, you find the best tree according to you find the best feature according to the information gain heuristic, and you partition the data into subsets according to that heuristic, and then for every partition, you recurse. Any questions? Yes.
Is ID3 algorithm considered as a learning algorithm?
It is. Is that the full question, though? Okay. It is a learning algorithm. Other questions? Yeah. It is. So, and the tree is the classifier. Because remember, if you have a decision tree, you can make predictions on future examples. And so it's a learning algorithm that produces trees. And in fact, here's an interesting exercise. I'll come to you in a minute. Remember the batches data that you saw in the first lecture? It would be a useful thing for you to do once you do your implementation for the homework and such things, if you're interested, try to run the ID3 algorithm on that data with some features that you invent. You might be able to find the same, you might be able to find the rule that you saw in class rather easily using this algorithm. Yeah.
I was going to ask, what's the expected runtime in the worst case?
So in the worst case, basically you have to use it's the number of, I'm going to do a crude approximation here. It's the number of examples times the number of features. And number of examples times number of features times number of values that the feature takes.
That's what makes it NP hard.
Well, the ID3 algorithm is not NP hard. It's actually fairly quick. What's NP hard is if you did not have if instead of greedy search, you wanted to find the single smallest tree that perfectly fits the data, that's NP hard. Yeah. This is not NP hard. This is fairly quick. Yeah.
So we usually store the decision trees, the algorithm using memory or through storage.
In this case, you store it in memory. I mean, usually these trees don't get very big. In fact, if your trees get really, really big, that by itself is a problem for other reasons. So for the most part, it's going to be in memory. All right. So now, in roughly the 15 minutes that are left, I want to talk about some practical issues that come up with decision trees. And we've already seen what decision trees are. We've seen the learning algorithm. And let's look at some extensions. In this part, I'm going to talk about some variants of this information gain heuristic. I'll be talking about one such variant. And in your homework, you'll be looking at one or two, depending on whether you're a grad student or not. And I'll talk about how to handle missing features. This discussion is not just about decision trees, but it turns out it's a useful place to talk about it. And with decision trees, remember, we can't handle features that are not discrete. And so how do you handle features that are numeric, for example? And we'll revisit that question. And the most important point here is this will be the first time this semester where I'll be talking about this idea called overfitting. Overfitting is a nuisance that we have to deal with any machine learning instantiation, and turns out decision trees are especially bad with that problem. So we'll talk about that. The information gain heuristic that we saw was defined in terms of entropy. It's entropy of the data minus expected entropy of this partition based on that feature. And the role that entropy plays there is it's a measure of impurity or disorder. It turns out there are other measures of impurity and disorder that exist, and they have been used for defining variants of the ID3 algorithm. There's something called the majority error. The majority error essentially says, suppose you stop growing the tree at this point. So you have a certain data set and you're not going to grow the tree anymore. You're forced to pick one label. The most reasonable thing to do there is to pick the most common label. And if it turns out that the most common label does not apply to all the examples, maybe there are examples that do not have that label, then by forcing the tree to just be that one label, your tree is going to make mistakes on all those other examples. So you could ask, what is the error that you get by picking the most common label? That's called the majority error. So if you have a data set with 15 pluses and 5 minuses, what's the majority error? .25. If you have 15 pluses and 5 minuses, you are forced to pick the most common label, you pick plus. That means on those 5 examples that are minus, you're going to make a mistake. So the majority error is 0.25. It turns out that this concept works very much like the entropy. Data sets that have higher disorder will have a higher majority error. Data sets that have all examples belonging to the same label will have a majority error of 0. And as the fraction of examples, as the disorder in the data grows, so does the majority error. And there's another one called the Gini index, which, in fact, here's a plot of these 3 things. So imagine that you have 2 labels, plus and minus. So if your fraction of positive examples is P plus is P, then P minus is 1 minus P. And so I can plot these things as a function of P, and the thing on top, the red curve here, that's entropy. Gini index is green and the majority error is blue. And notice that all of them have a similar sort of a shape. When P is 0, all of them are 0. When P is 1, all of them are 0, and they peak in the middle. They peak when there's maximum uncertainty. When P equals half, all of these things have the highest value, and they take the lowest values when the uncertainty is the lowest. So you can essentially drop in majority error or Gini index or other measures of uncertainty in place of entropy to define variants of the decision tree algorithm. And in fact, you'll be doing that for your homework. Each of these work like entropy. So the interesting question to think about is whether it actually makes a difference in the trees that you grow. You'll be thinking about that also in your homework. Questions? One thing to mention here is the examples I'm using in this part of the class involve binary classification, right? You have plus and minus. I'm sorry, in your homework, just to make things a little more complicated, we've given you a multi-class classification task. But the definition of entropy still works. It's simply the sum over all categories of P log P and the negative of that whole thing. So everything just works out of the box. You have to just make sure that your code is not hard-coded for 2 labels. Questions? Yeah.
Remind me again, for entropy, anytime you're saying log, you're meaning log base 2?
That's right. For entropy, anytime I say log, I mean log base 2. And for the rest of the semester, anywhere else I say log, I mean I mean natural log.
Got it.
For historical reasons, entropy is always log base 2. It should not really matter because all we are doing is ranking the feature, and the log base 2 or log base anything will not change the relative order of the features, but it will change the values that your code produces. Okay, now let's consider another problem. Suppose you have a data set where for some reason you do not have the value of a feature. So consider this day number 8 here. Maybe on that day, the humidity meter broke down, and so you could not record that feature. So you don't have the value of that feature. What can we do? Any ideas? What can you do to handle such situations? Yeah.
Drop the row.
One option is to drop the row. But I would recommend against that. Because if you drop the row, then you're losing information about the correlations between the other available measurements and the label. So what can you do that does not involve dropping the row? By the way, you can drop the row if you have a ton of data. But if, let's say, data's not that abundant, yes.
Well, like surroundings, like, like a day where it's like snow, sunny, hot, and
That's an interesting idea. So let me repeat that. You look at the neighborhood of that and ask, can we somehow fill in that feature value on days that are also sunny, mild and weak, right? We don't have another example of that kind. But essentially, you are trying to compute the value of that feature using the other information that you have. Did someone else? Yeah.
Can we pick like the most common occurrence, like humidity?
You could do that. You can pick the most common occurrence, and in this case, it will be high. Yeah. Same thing. Did you?
You could just make so it won't branch on that unless it's like a majority. Like unless it's.
So you change the learning algorithm so that it prefers not to branch on humidity. That's a tricky.
With the exception.
But that's a tricky thing to do. But what if humidity was the right thing to branch on? And because you're forcing it not to branch on it, you're kind of introducing an artificial sort of complexity in the tree. That's tricky. I would recommend don't change the algorithm. It's safer to change the data or do something with the data. Yes.
you could discard the entry in the data, say we're not going to use this for training.
Yes, that was also the first answer. I would not recommend that if you don't have a lot of data. Sorry, I would not recommend that unless you have a lot of data. So the most common things that are done are, that's another answer on Zoom. Maybe you can treat that as its own value. Maybe humidity does not take two values, high and normal. It takes three values, high, normal, and unknown. That's also a reasonable thing to do. Sometimes you might have to, you're forced to do that. It might lead to problems in other cases, but all of these methods involve, everything that was suggested involves an assumption. And this is an assumption that says unknown is a different type of humidity. So some ideas that I just put together on a slide. One idea is to use the most common value, which is, in this case, in this column, the most common value is high. So you pretend that the question mark is high. Another example is, another situation is, you don't want to look at the most common value among all these examples. You also have the label. So you only look at those you know that the label of this row is no. So you look at those examples where the label is no, and you take the most common among those alone. Because in some sense, these are similar examples. You could have defined similarity in other ways also. Maybe you want to define similarity based on the feature wind. That's related to the first suggestion where you use neighboring features. And among those three, turns out also high. So you could do that. Another sort of a complicated answer involves using fractional values for this feature. So you could use, okay, I'm not going to go into that because it's complicated and it does not give you additional benefit So let's skip that for now. What can you do at test time? So let's say now you've trained a decision tree and you're trying to use that decision tree on a new example. And on that day that you want to use the decision tree, the humidity meter broke down. What can you do then? Yeah. You could pick the most common branch for that particular feature. Or that's actually a very reasonable idea. Any other? You could just hard code the fact that humidity is the most common thing in the day, high is the most common value, and any unknown value is treated as high. Essentially, you use similar sorts of ideas, similar sorts of intuitions to do what's called what's known as missing feature imputation. You use neighboring values and other features to estimate, or maybe other examples to estimate the value of the missing feature, and you fill it in whenever that feature goes missing. In the 4 minutes that are left, let's consider the case where the features are not Boolean. We've already seen this. The feature sunny, the feature outlook can take 3 values: sunny, overcast, or rain. So your trees don't have to be binary trees. Your trees can be these sorts of multi-way branching trees. But it so happens that even if you have trees that are, even if your feature takes multiple values, you can convert these sorts of features into binary by converting this one feature called outlook equals sunny into three different features. Outlook sunny is true, outlook overcast is false, and outlook rain is false. So this one feature gets blown up into 3. And then you get only binary trees. Now, why would you do that? Because this is a rather extreme case, but by doing this, you can actually convert your trees into rules easily. And then maybe you want to do something interpretable with the rules later on. But the more interesting sort of non-Boolean situation is for numeric features, and we've already encountered this. If you have features that are not discrete at all, that you have numbers like height and length and such things, the most reasonable thing to do there is to use ranges to decide upfront, using the data or maybe using some intuition. You come up with strategies to bucket the data, bucket that feature into ranges, and then you ask, is this particular feature between 0.5 and 0.7? Is it between 0.7 and 0.9? Is it more than 0.9 or is it less than 0.5? This could be, I just created 4 ranges. How do you come up with those 4 ranges? That's a bit of a guessing game. You could use some domain knowledge. You could use your data to decide the ranges and such things. I'm not going to talk about that right now, but if you're interested, we can talk about it in office hours. We have 2 minutes left. And we have a huge concept to talk about, overfitting. I'm not going to introduce that concept, but I just want to introduce an example. Consider this function. We're calling it the first bit function. It's a Boolean function that takes n inputs, and the label is simply a copy of the first input. All the other features are irrelevant. So if you have 2 inputs, x0 and x1, the label is simply a copy of x0. Can someone tell me what's the decision tree for this function? Yeah. If x0 is false, the label is false. If x0 is true, the label is true. It looks something like that. Now, this is just the only reason I introduced this, and I'm not going to talk about overfitting, is you already seen the decision tree learning algorithm, right? Imagine you take this data set and give it to the ID3 algorithm. As an exercise, I want you to convince yourself that ID3 will generate this tree. It will pick that feature. No matter how big this table gets, no matter how many features you have, for this particular data set, ID3 will always pick that one feature that's relevant. The reason I'm introducing this and not going into overfitting, but I want to introduce this is because turns out this is a very useful debugging tool for your code. The information gain of the relevant feature will be the highest. Okay, I'll stop here. On Tuesday, I'll be using this function to talk about overfitting. You don't need the remainder of the slides for the homework. Everything you need for the homework, we've already covered in class.